Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video starts a series on the Law of Cosines, which is also known as the Generalized Pythagorean Theorem. We start this video, or actually this series, with just the theorem itself and the proof. Note, the theorem for the Law of Cosines is, just like for the Law of Sines, for any triangle, not just right triangles. It does work for right triangles, however, but it's more than just for right triangles, it's for all triangles. If you look at a textbook will have 6 versions of this. I think that's way overkill. So I only use or show one version of this, and I assume that you can derive, or not even derive, that you could just use the other 6 immediately. The ones that you'll often see listed out in a textbook are the following, and I think that's way too much in the way of overkill. I'll just show you how to think of this without knowing all of these other formulas. It's just much easier to just know the one. The general idea works like this. Somebody hands you a triangle. You can label this triangle any which way you want. It doesn't really matter unless they specifically state, like for example, one vertex is really large as far as angles go. But other than that, it really doesn't matter how you place your letters. So I'm going to call this A, B, and C, and therefore side A, side B, side C. Now, if somebody came in and they said, oh, you know what you have? You have, let's just pretend, angle A and maybe side B and side C. So I'm going to highlight those. Let's say that somebody tells you you have that angle, that side, and that side. Well, I will say the missing side, the side that I want to find, I'll maybe actually circle it up in red. That side is what I want to find, right? So rather than stealing this formula, or maybe I should say, rather than memorizing a bunch of different versions of this formula, I'll just write it slightly differently. A squared is equal to B squared plus C squared minus twice BC cosine of the angle opposite this side. That's how that works. Whatever this side is, its opposite angle is right there. The rest of the stuff really involves the other sides. So the sides that we're not trying to find, which are B and C, are all listed cleanly right there. Notice in that equation, again, highlighted, I have all the stuff I know highlighted there, and we can easily find A by taking the square root of both sides. Now, what if instead of all of that, so let me go ahead and just erase all that instead of backing out of all that. What if instead somebody said, you know what, I didn't give you, let's say angle A and side B and C, but instead I gave you angle B and side A and side C. Well, and they ask, find side B, for example. Again, I would just say, okay, great. That's missing side B squared is the same thing as A squared plus C squared. Well, sort of. That would be the Pythagorean theorem, but if it was a right triangle. But we're going to make an adjustment because it's not the Pythagorean theorem, it's the generalized Pythagorean theorem. And our adjustment is subtracting twice A times C, this A and that C, times the cosine of the angle opposite that missing side B. Now, of all this information, again, we know A and C, and we know angle B. So again, we can find that missing side B by taking the square root of both sides. Now, this is not a proof. I haven't done a proof yet, but I just want to make sure that you understand that once you have one version of the equation, you have all versions of that equation. Let's try one more before we go into the proof. Let's suppose instead that somebody hands us all three of these sides. And they say, for an example, find angle B. Oops, maybe I should not use that. Maybe I should use red. What if they said find angle B? Great. Well, I want to use the law of cosines, and I want to have an angle B, not an angle C. Well, that's okay. If I put an angle B there, then the opposite side should be on the left-hand side. So that is, side B squared should equal some stuff with a cosine of angle B. And that some stuff is all the other stuff, right? A squared plus C squared. And then offsetting that with twice AC times, and then the cosine of B. Remember, the things we know here would be side B, side A, side C. So we know all this highlighted stuff. There's no need for me to teach you another formula because you know how to subtract and add. You know that you could just subtract A squared from both sides. You could subtract C squared from both sides. You could even divide both sides by a negative 2AC. You can even take the cosine inverse of both sides. And you would have angle B. So this is my way of saying all you need really with the generalized Pythagorean theorem, or in other words, the law of cosines, is a single formula as a template. Once you have that single formula, you have everything you need. Now that all being said, let's go ahead and dive into the proof of the generalized Pythagorean theorem, or in other words, the law of cosines. First thing I'm going to do is I'm going to actually get rid of these highlighting here and here as well, and also there. And I'm going to draw in an altitude. That's usually a basic step in any type of proof involving triangles. You just draw in a quick little altitude there. And the altitude I'll call H. It's distance H. And what I'm going to do down here, see, I've drawn in that altitude. I've created two right triangles, that right triangle and the other right triangle. And I'll call this length right here, I'll call that X. Just don't know that length, but so I'll call it X. But if you have that length, X, then the rest of that length, well, remember the full length of this side here, let me highlight it. The full length of this side is B. If X is taken up for this part of it, then the remaining part is B minus X. So this is B minus X. That's the remaining part. If you add those two together, you get B minus X plus X, which is B. So that should make sense. And what we're going to do here is we're going to use the Pythagorean theorem. Specifically, I'm going to use the Pythagorean theorem on the right triangle here. This triangle, and maybe I should just maybe use red. This triangle right here. We're going to use Pythagorean theorem on that triangle. And if we did that, we would get that A squared is equal to H squared plus the quantity B minus X being squared. That's pretty good. And what I'm going to do is distribute out that binomial. So this is plus B squared minus 2BX plus X squared, whatever that may be. However, at the very same time, if I wanted to, I could look at this other right triangle right here, and I could note that, so I'll say and, C squared is equal to X squared plus H squared. So we have these two formulas here. We have A squared is equal to this ugliness, and we have C squared is equal to that other ugliness. Well, wait a second. Don't you see in this picture we have an X squared and an H squared, just like we have an X squared plus an H squared there? Well, that's kind of cool. So let's go ahead and replace that H squared plus X squared in the top box with C squared. I'll go ahead and do that right now. I'll just say this implies that A squared is equal to, I'll write the C squared off the back end. So it's just B squared minus 2BX. And then again, that yellow highlighting is actually just a simple C squared. And in fact, I could just say A squared is equal to B squared plus C squared minus 2BX x. But I'd really like to know what x is. Well, x is not too terrible to find. I'll use that green triangle to find out what x is. If you take a look at this green triangle, remember this angle here is angle A. We could say the cosine of A is x over c. So, but the cosine of angle A in that triangle is just the same thing as x over c. Or in other words, x is equal to c times the cosine of A. Well, let's go ahead and replace the x in this formula with this version of x right here. And we will be done at that point. This implies that a squared is equal to b squared plus c squared, very much like the Pythagorean theorem, but we have this minus 2 times b times x, but x is c cosine of A. That is actually the proof of the law of cosines. Yes, I understand that in our theorem up above, I have it as c squared is equal to a squared plus b squared minus 2ab cosine of c, but I could just move these letters around any which way I want. I will get that. I can get any version of the law of cosines that I want just by moving things around. So this is actually the proof of the law of cosines, QED. Again, if you wanted to, you could totally prove this for c squared is equal to a squared plus b squared. Just rewrite this whole thing with angle C right here and angle B right here. So that this side that we're missing is side C. This would be side B. And these lengths, that length right there would be C minus X, and you would get the same exact proof. All right, now that we've proven the generalized Pythagorean theorem, or the law of cosines, we're going to stop this video for now. And in the next video, we'll start using the generalized Pythagorean theorem, or the law of cosines.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much, that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry. Don't whine, just